Any questions about anything from last time? I've got a new microphone up here that should take away the high-pitched whistle you might have heard in my Boilercast recordings. So that's an improvement, maybe. Were there any questions about anything? Well, today's a beautiful historical thing called Bessel's inequality. Bessel is another person who's in my family tree in the math world. On the other side, the German side instead of the French side. And I'll explain what it is in a minute. There's real versions of Bessel inequality, and there's complex versions, and they're basically the same. I'm going to do the real version today because it's just easier to write out, and there's no annoying conjugates in any of the formulas, so it'll make it a little bit easier. But I'll mention at the end that the same thing works in the complex case, and it really is the same, except you've got to keep track of your conjugates and play a few more games there. So in the real inner product, of course, the f and the g are real valued. Okay, so let me explain what Bessel's inequality is. Holds in quite general terms. Fourier series are just one kind of orthogonal expansion. It's possible to expand in other things. Bessel himself was studying Bessel functions and took orthogonal expansions in terms of his Bessel functions. And so naturally he had to study this. This came up in his studies. And what we'll assume here is that we've got functions, I'll call them phi sub n, of x, are continuous, real valued, functions on an interval, AB. Think minus pi to pi, if you like, that are orthogonal. Meaning that their inner product is 0, pairwise 0. Meaning that when you inner product phi n with phi m, I want to say not orthogonal, I'm going to say orthonormal. That's a new word today. Orthonormal. And so it means, number one, they're orthogonal. So the inner product there is going to be 0 when n is unequal to m. They're orthogonal. And the new thing is that when I inner product phi n with itself, of course, that would be the integral of phi n squared. If phi n isn't 0, that is not 0. The 0 function is not allowed in these things. So, and in this case, I'm going to assume that this integral is 1. I can always normalize my functions to make that the case. Okay, so that's where the word normal comes in. They've been normalized so that integral is 1. So a remark, let's see. What am I going to do? Okay, I'm getting ready for... I'll make a definition here before I continue. Definition. The L2 norm. This is the L2 norm of a function phi is the square root of phi n inner product with phi inner product with phi. Of course, that's the integral. That's the square root of the integral from a to b of phi squared dx. And a remark is to get that integral there that you want, you can always normalize. So here's a remark. I can always normalize an orthogonal family of functions we've seen an example of such a thing such as sine nx, the sine functions in the sine series on the interval from 0 to pi. A family of functions by dividing, let's see, that's by their L2 norms. It'd still be orthogonal. So I would get a new one, say phi n twiddle would be 1 over Cn phi n, where the Cn is that norm. So these would be orthonormal. Now that I've normalized them. And these things I started with were just orthogonal. They'd still be orthogonal after I divide out those constants, because constants can pull out of an inner product. In the real case, there's no conjugates to think about. Okay, so what we're hoping when we do this, we're hoping that we can expand any old function in terms of an orthogonal expansion. So we're hoping to be able to expand a general function in terms of things like the sine nx functions. Like the Fourier series case. Okay, so if we could do that, here's one reason the normalization is nice. So remember, if I could expand it like that, then when I inner product the left-hand side with one of the phis, that would be, hope I could distribute that integral through the sum and get the sum of phi n inner producted with phi m. And most of those are 0. In fact, all of them are 0 except one. These are all 0. If n is unequal to m. And so this inner product would spit out, let's see, the only ones that's not 0 is Cm rather, phi m inner product with phi m. That's the only one that's not 0 in that sum. And so we see that if f can be expanded like that, then the Cm has to be if f equals that expansion, then the Cn has to be, oh, by the way, this phi sub m, this is normalized, and that's why I did it. That thing's equal to 1, and so the Cm has to be, the Cn would have to be f inner product with phi n. Okay. Okay, so now I'm going to make, this is going to be a definition in my formulas for today. So today, I'm going to make Cn be defined to be that thing. Define Cn to be f inner producted with the nth orthogonal function. Okay, so the Bessel's inequality, getting closer to being able to say what it is. The big fact for today is that if I take a partial sum out to n of Cn phi n, is the best L2 approximation to f on the interval AB. Okay, so among functions that look like that, among functions of the form, these are like trigonometric polynomials, a sum of from 1 to n, and now I'm going to put it here instead of c's, I'll put an's. So if I take any other an's that then this might be different than the cn's, I get not as close in the L2 sense. Okay, that turns out to be pretty important. So what does that mean? That means that if I were to take the L2 norm, that's the integral thing, f minus this best approximation, that L2 integral norm would be less than or equal to the same thing if I take my general trigonometric polynomial-like thing, with an an instead of a phi n. And the only time I could get equality is if the an's were all equal to the cn's. With equality only when cn equals the an, or I should say an equals the cn. Cn's are defined, an's are can be any old thing. For n equal 1 through n. And furthermore, this is the Bessel's inequality. Furthermore, the sum is n equal 1 to infinity. Let's say I'll just do it with n first. The sum from 1 to n is less than or equal to of n squared, that's a positive thing, is less than or equal to the norm of f squared. Okay, and you learned in Math 341 that a non-decreasing sequence of positive numbers that's bounded above has to converge. So an exciting moment here is, aha, the sum, as n goes from 1 to infinity, cn squared converges to something. To a limit which is less than or equal to f squared, norm of f squared. And that's exciting because that's going to mean that the Fourier coefficients of a continuous function tend to 0. So if a sum like that converges, the terms have to go to 0. And those terms are going to be Fourier coefficients. So we'll get a corollary, very important thing. Sometimes this is called the Riemann-Lebesgue lemma. But the Fourier coefficients of a continuous function f on the interval from minus pi to pi tend to 0. As n goes to infinity. Meaning that the an terms go to 0 and the bn terms go to 0. And of course, so do the complex versions. I'll say so do the complex versions. Do the complex CNs. Because they were just simple combinations of the ANs and BNs. So do complex versions CN tend to 0 as n goes to plus infinity or minus infinity. Because they're just simple combinations of the ANs. Sums of ANs and BNs. So that's exciting to know. And let's see, why is that kind of a interesting thing to think about? If somebody asks you to show that Fourier coefficients go to 0, your first inclination would be to look at the integral and estimate it. Okay, that's not obvious. Because if I look at the Fourier formula Why don't I pick one? I'll do a Fourier sine one, maybe. If I write a Fourier sine coefficient, remember that's 1 over pi, integral from minus pi to pi, f of x sine nx dx. Okay, so it'd be natural if I'm going to estimate that to just do the basic estimate for integrals. I take the modulus here, not modulus, but absolute value. And then I'd use the basic estimate for integrals here and get that this is less than or equal to 1 over pi, integral from minus pi to pi of f of x times sine nx dx. Okay, if f of x is continuous, it would be bounded. So I could at least bound this by something. That's because f would be bounded. And sine nx wiggles up and down from plus and minus 1, so this term is less than or equal to 1. And so that integral would be less than or equal to 1 over pi times m times 1 times the length of the interval. And that's not zero. That's not going to 0. There's no n in there. So I get that it's less, this is equal to 2, this thing is equal to 2m. And that means, ouch, I didn't see that it goes to 0. Does not tend to 0. So there's something subtle happening. And in fact, if you think about what it could possibly be, let's take a function, random thing. Let's, I'll just make something up. Here's minus pi. Here's plus pi. I'll make my function wiggle around like that. I'll do something fun now that I learned recently. I'll take that. And now I'm going to mess around with it. I'll turn it green. And I'll turn it inside out. Oops. I'll grab this end and flip it upside down. There. Does that look symmetric? Okay, this blue one is f of x. And the green one is the minus f of x curve. And if you think about sine nx, it wiggles like crazy. And it wiggles up and down between plus and minus 1. And so let's see, it's 0 here. When I multiply this blue thing by the sine function, it would be 0 there. And then when it's 1, it'd be on the top curve. When it's minus 1, it'd be on the bottom curve. So this thing is sine of 0 sine of 0 was 0. That's good. My sign looks awful. Maybe in my office I'll make this look better. That's not too bad. That purple stuff is f of x times sine nx. It wiggles up and down between the top curve and the bottom curve. And if you think about integrating that, the humps that are above the axis look like they would roughly exactly, I guess there's no such thing as roughly exactly, cancel the areas on the top. So they'd be negative and they'd cancel. And so that's exactly probably what's going on with that, the coefficients going to 0. So, looks like area under the positive humps cancel the area under the negative humps. Or vice versa. So that's the gut feeling about why Fourier series tend to zero. Fourier coefficients. That's the intuition. Okay, well, I'm going to give you the demonstration rather than the intuition. Intuition is nice, but it's not a proof. Okay, so here's the proof of Bessel's inequality. I'll write E star is that thing I want to estimate. I'm gonna square that thing I want to estimate. So that'll be F minus the sum from 1 to capital N of Cn phi n. And I'm going to square it. So I don't have to write those big ugly square roots. Remember that norm is the square root of something, and when I square it, that norm squared is going to be the integral from a to b of f of x minus the summation of Cn phi n squared. And I'm going to write that squared like this. So that's going to be the sum as n goes from 1 to n. And then I'm going to write the same thing, but this one I'm going to use m's instead of n's to make it easier to multiply this mess out. That's just a square. Okay. Well, let's see. Now I'd have to multiply that out. The easy thing is going to be the f squared term. That will be f squared dx. And let's see, then I would get minus a sum as n equals 1 to capital N. I can pull out the Cn's. And I would get integral of AB of f times phi n dx. That's the CM's. That's wait a minute, Cn, yeah. This is also a Cn. So that's where the squares come from. That's what the Cn's were defined to be. So I'm going to get a squared there. I'm going to get another one of those things. Let's see, I'll get minus a sum as n goes from 1 to n of the CM's times a similar integral. Once again, that's a CM. I should have given myself more space. I guess now I'm going to get a sum as n goes from 1 to capital N and a sum as m goes from 1 to capital N of the integral, let's see, Cn times Cm times the integral from a to b of phi n times phi m. Most of those are 0. So, in fact, they're either 0 or 1. This is the delta function. Delta nm. which would equal 0 if n is unequal to m, and 1 if n equals m. Minus. Yeah, so let's let, what did I get here? Let's let S be a sum n equals 1 to capital N of my Cn squared. Notice it appears there multiple times. So far, what do we get? I got my f minus the summation of Cn phi n from 1 to n squared equals the integral from a to b of f squared dx. That first one is a minus my sum. The second thing there is another minus my sum. And this, the delta thing, is a plus the sum. Okay. How exciting. That is equal to the integral from a to b of f squared dx minus my sum. And this thing on the left, being a norm squared, is greater than or equal to 0. And it's equal to that thing on the right, which means that this thing is greater than or equal to 0. And when I put the Cn on the other side, I get the inequality, famous Bessel's inequality. Bessel's inequality follows when I put that Cn, sum of the Cn squared on the other side, I get summation n equal 1 to capital N of the sum of squares is less than or equal to this thing, which is clearly a positive thing. That is the demonstration of Bessel's inequality. Okay. And I promised that I'd show you that this is the best you can do in that inequality. And I'm going to be sneaky about how I do that. Questions about this before I do that? It's pretty straightforward calculation. It just gets kind of messy writing it all out. Let's go back up here and start over again. I can only do this with this kind of a tablet. I'm going to go back and start over. And in place, I'll call, instead of E star, I'll call this E. E is going to be, instead of using the CNs, I'm going to use ANs. Okay. And when I get to this next part, interesting, these are going to be now ANs. And these are going to be AMs. And so in the next spot here, this one is going to be an AN. But interesting, this other one that I made in red there, that's still going to be a CN. And this other one in red is still going to be a CM. But this one's going to be an AM. And here, this one's going to be an AN, and this one's going to be an AM. But I'm still going to get the delta function there because those are phi n and phi m. And so what am I going to get? Let's see. Let me okay, so let me show you what I got. E when I go back and look at that, I'll write out what my E is. My E turns out to be the L2 norm of F squared. And then I get minus 2 times, kind of looks like an inner product, ANCN. And then I get plus the sum as n goes from 1 to n of AN squared. Okay, that's what if I did the calculation over again with ANs in terms of CNs, that's what I would get. And the E star I got the first time, that was F squared minus the summation of Cn squared. Those are the two results of the two calculations. What? What? I can't hear you. Yeah. N. That goes to N. Thank you. Well, I claim that E is the best. No, I'm sorry. E star is the best. So E star is going to be what? E star is the best. So E is going to be even bigger than E star. So I'm going to take E minus E star. So this is the aha moment for Bessel. If I take E, which is worse, than E star, which is the best, we're going to see it's best. I write out this mess, and it's, let's see, so I'm going to tell you, you get that algebra. You look at it, you stare at it for a while. Oh, this is before I stare at it. When you write it all out, you get the sum. Yeah, notice that the F squared parts cancel, and I get an algebra thing. I get a sum of n squared minus 2ANCN plus AN squared. And you stare at that for a minute and realize, aha, that's a square. That is Cn minus AN squared. And a sum of squares is greater than or equal to 0. Okay, that means that that's strictly, let's see, so what do I see? I see that E minus E star is greater than or equal to 0. Meaning that E is not as good as E star. Well, I should say that E star is less than or equal to E. And of course, that thing is so we see that E is worse. And now you think about, what if E was equal to E star? What if E equals the best? Well, I'm adding a sum of squares. The only way that could be 0 would be if each term was 0. Only happens if each term is equal to 0. And that would mean that Cn minus An squared equals 0. And that would only happen if Cn equals An for n equal 1 through n. Check. So that we only get equality when we have the best approximation. Okay, so let me do some quick examples here. Let's do an example, the example. Let's take 1, so it's going to be my trig functions, Fourier series functions, cosine nx and sine nx. And when I divide by that thing to normalize it, I would have to divide by 1 by the square root of 2 pi. I'd have to divide cosine by pi, square root of pi, and sine by square root of pi. And this would be as n goes from 1 to infinity. 1, 2, etc. Those are orthonormal. So you see that those things in the Bessel's inequality are just the Fourier coefficients. They're orthonormal. And if I wanted to use my notation, I might say, okay, phi of 1 of x is the constant function. And then I'd write phi of 2n of x, let's see, 2n. Yeah, phi of 2n of x is the cosine one. And then the sine ones would be phi of 2n plus 1. Then those would be, then if I did it like that, it'd be absolutely the same as my Bessel's inequality situation. I'd have a phi 1, phi 2, phi, etc., and they would be orthonormal. So let's see, the inequality is, when you do it, there's coefficients that are kind of annoying. I'd get 2a0 squared plus the summation as n goes from 1 to infinity of an squared plus bn squared is less than or equal to 1 over pi times the integral from minus pi to pi of f squared dx. That's Bessel's inequality in the context of Fourier series. Yeah, it's infinity. It'd be true for each n. And I could let n go to infinity. So that's Bessel's inequality for Fourier series, for the full Fourier series. There'd be one for the sine series and one for the cosine series too. And a mind-blowing thing is that for Fourier series at least, that turns out to be an equality. So it's a big fact. For Fourier series, Bessel's inequality turns out to be an equality, and in the case of equality, turns out to be an equality. And the equality is called Parseval's identity. And the reason is that that orthonormal thing is a complete orthonormal basis. So the reason the Fourier functions form a complete orthonormal. And if you remember a word from linear algebra, basis for L2 from minus pi to pi. That's the space of square integrable functions on interval from minus pi to pi. That's a Hilbert space. We don't know these words yet. In fact, I'm only going to mention them. We'll be able to do things without having to go into Hilbert space theory. That's the Hilbert space, the original Hilbert space of square integrable functions on the interval minus pi to pi. And the mind-blowing thing is that we can think of the CNs like coordinates. So the great advance of Hilbert space theory is that we can think we have a function and we send it to a sequence of points, C1, C2, C3, dot, 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 etc. And they act just like coordinates. It's just there's infinitely many of them. They act just like coordinates. And in fact, what we see when we do this is that we get an isomorphism. What do we get? The Fourier series thing. This would take, we would get an L2 norm here. The norm of f squared, that would be the integral from minus pi to pi of f of x squared dx. And that would equal, by Bessel's inequality, the sum of the Cn squared